design variable of mu to optimize the vibration properties. And then you're given M inverse K
Can you repeat that?
is equal to mu minus K mu.
You?
Yeah, the Greek letter mu. Okay. And then we're asked to compute the damped natural frequencies of the system in terms of mu and K. And it says, note that omega d is equal to omega n in this case because we're ignoring damping, so it was needless to say that. Therefore, it's just we're calculating the natural frequencies. So we're given our M inverse K, which is good. Lynn's exams are confusing because he puts a very long problem statement that is trying to confuse you, but your job is just to extract the relevant information, which was you're using mu as a design variable, and then you're computing the natural frequencies in terms of mu and K. So what's the first thing we're going to do is, since we already have this, we can just go straight to our eigenvalue problem, right?
Mm-hmm.
Yeah, so that's what we're going to do. I'm going to just go ahead and write out what we got, because that has options in terms of x, in terms of omega squared, and in terms of our M inverse K. So that's perfect. I'm going to write M inverse K minus lambda I, where lambda is equal to omega squared, x equals 0. And further, we're just looking for the lambdas, so we're going to say the determinant of M inverse K minus lambda I is equal to 0. So what we're going to do is we're going to set up the matrix M inverse K minus lambda I. And that's going to look like this. All we're going to do is just subtract the lambda from each of the diagonal elements, which is going to be mu minus lambda, negative k, mu minus lambda. Now, the determinant of this matrix is equal to 0. So, now what we can do is we're just going to take the determinant of this. Determinant is diagonal values, the product of the diagonal values, minus the product of the off-diagonal values. So when you write that, you're going to have mu minus lambda times mu minus lambda, so far so good, minus negative k times negative k equals 0. So now we've got one expression like this. It's out of matrix form. We're going to try and make this into a polynomial in terms of lambda. So FOIL, first to second, mu squared minus 2 lambda mu plus lambda squared. Negative k times k is k squared, so you got minus k squared equals 0. All right, you've got this expression. Now we want to rewrite it in standard quadratic form, which is going to be mu squared minus 2 mu lambda plus mu squared minus k squared equals 0. Awesome. So now we've reduced this down to a single quadratic equation, and what are we going to do? We're going to take the quadratic formula. So let's sing it together. I'm just kidding. So quadratic formula is negative b, which is going to be 2 mu plus or minus the square root of b squared, which is going to be 4 mu squared, minus 4 times a, which is 1, and then c, so minus 4 mu squared minus k squared. Take the square root of this, all over 2a. 2 is just going to be equal to 1. Therefore, we have 2. Okay. These are our eigenvalues. So now we're going to go ahead and simplify this. This is going to be minus 4 mu squared plus 4k squared. Right? Look at this. These mu's are going to cancel. Awesome. Okay. And now we've got, these 2's are going to cancel, so now we've got lambda is equal to mu plus or minus the square root, or 1/2 times the square root of 4k squared. Now, if we factor this 4 on the outside, that's going to be a 2 on the outside. Therefore, we're just going to have the square root of k squared. And now our eigenvalues are just mu plus or minus k. And when we want to take the natural frequencies, this is the most important part. That's omega squared. Therefore, omega is equal to plus or minus, or excuse me, it's going to be the square root of mu plus or minus k. That's our answer right there. You will get points off if you do not do this last step right here, where you take the square root and find the natural frequencies, not the eigenvalues. So remember the 11th commandment here, that lambda is equal to omega squared. Make sure you arrive at omega, because that's what he's asking for. Does this make sense? Any questions on this problem? So the only thing we're given in this problem was our m inverse k. And so it was up to you to realize that we could set up our eigenvalue problem. We move it to where we have just the determinant of m inverse k minus lambda I. We set up that matrix, take the determinant, get this to the characteristic polynomial. That's what the name of this expression is called. Solve for the roots of that, which are lambda. Take the square root of the roots. That's how we get our natural frequencies. Any questions? Are we good? Tracking? Am I using that slang right? Okay. All right. Next problem. This next problem is it's deceptively simple, which means that it's a very long problem statement.
Wait, so for the last question, all it was asking you to find was the natural frequency?
Yes. Find the natural frequencies.
You just
In
get that
terms
from the
of
eigenvalue.
mu and k.
Yep, and that's exactly what we have. Natural frequencies in terms of mu and k.
Yeah, that's for natural frequency, you just get the eigenvalue, same
Wh-
thing,
wh- What's the, why do we take the determinant?
It's just-
So it is a matrix, right? These matrices are obviously non-trivial, which means that not all of the values are equal to 0. When we're saying a matrix minus a matrix is equal to 0, we're just going to take the determinant. This is one of those things where it's like deep linear algebra knowledge instead of just for this one, so just trust me when I tell you, when you're trying to find the stuff on the inside of this expression, you're going to take the determinant.
It's a good answer.
Yeah,
It's a good
just trust me on this
Yeah.
one. Okay, all right. Okay. So I'm going to read this problem statement. So that last question was worth 15 points. This next question is worth 45 points. Okay. Your parents have so embraced the exercise and fresh air resulting from their new bicycle built for two lifestyle that they're now trying to be extra healthy in other aspects of their lives. They have recently started biking to the farmer's market for fresh vegetables. However, they are now realizing that the extra weight of those fresh vegetables changes the vibration properties of their ride. They have installed sensors to measure the displacement at 4 locations on their bicycles such that x1 is the displacement at the front seat, x2 is the displacement at the back seat, x3 is the displacement at the vegetables basket, and x4 is the displacement at the back wheel. After riding with different amounts of vegetables, they found the mass that results in the best quality of ride. Then they recorded sensor data of the vibrations during this ride with the optimal mass of vegetables in the basket. You're then given a chart of 4 periodic sinusoids where time is the dependent variable, and then amplitude, x1, x2, x3, x4 are your dependent variables. You are able to help them understand the situation by doing a modal analysis to find the mass matrix and stiffness matrix. And then you're given the M inverse K matrix. Compute the mass M3 of the vegetables in the basket that gives this optimal ride, having omega equal to the square root of 10 radians per second. So what I'm going to do is I'm going to go ahead and draw out all of the things that we're given. So the first thing is that omega is equal to the square root of 10 radians per second. That's the first thing. The next thing is our M inverse K matrix, and it's a 4x4. So we're going to have 1, 75, 5.5, negative 0.5, 0, 10, 0, 0, 0, 1600 divided by M3, 20 divided by M3, 0, 0, 95, 0, and 0.5. This is our M inverse K matrix. And then, finally, we're given a graph that looks like this. And I'm going to try and draw this to the best of my ability. I'm much better on pencil and paper than I am on whiteboards, so please forgive me. Okay. So we're going to have x1, we're going to have x2, we're going to have x3, we're going to have x4, and we're going to have time in seconds, and then we're going to have 2, minus 2, 0.1, negative 0.1, 2, negative 2, and then 1, negative 1. And then each of them looks like this. And so they say that 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So this is all the information we're given. Now, what we need to recognize is we're given omega squared, or omega, we're given M inverse K, and we're given 4, essentially what we can do is we can represent this bicycle as 4 parallel mass spring systems that are coupled, because they're all part of the same bicycle. Therefore, what we can do is we can realize that this graph is going to hold our mode shape. So what we want to do is want to go ahead and write what our mode shape is by extracting the amplitudes of these graphs. Because notice how each of these is going to have a period of 2 seconds. So t equals 2 pi over omega, which is going to be equal to 2, is going to cross out, therefore omega equals pi, which is actually very close to the square root of 10. Okay, so since each of these have the same frequency, that means that we know for sure they're also part of the same mode. And now what we're gonna do is when we look at this graph, we're gonna extract the relative amplitudes of each of these at the same time. So what we can do is we can declare our mode shape to be 2, 0.1, 2, and 1. So 2, 0.1, 2, and 1 is our mode shape. This is what we have right here. And guess what? The best part about this problem is that now that we've extracted all the relevant information from this graph, we literally don't need it anymore. And that's perfect. So all that. So Lynn does that pretty often where he'll give you some graphs and all you're supposed to do is be able to interpret them very quickly like that. So all that graph was just to give you this, so that you could recognize that. What's up?
Why did you mention period equals 2 pi over?
I was checking
In case
it.
they didn't give us the period.
Exactly. If they didn't give you the natural frequency, that's how you could extract it right there. Is
Oh, so
look at the period,
2 equals 2 pi over.
yeah,